Hey everyone, and welcome. If you've ever really dug into physics, you have definitely heard of I.E. Irodov. His problem book is legendary, packed with questions that really push you to think. Today, we're cracking open a classic from that book, Problem 1.27. So let's dive right in. So, here's our game plan. First, we're going to make sure we understand exactly what the problem is asking. Then, we'll review the physics tools we need. After that, we'll connect those tools to the equation we're given, and finally, we'll calculate the velocity and, most importantly, talk about the bigger lesson here. Okay, first things first. Before we can even think about solving anything, we have to be crystal clear on what the problem is giving us and what it wants in return. And here it is, the problem itself. So we've got a particle, it's moving with a constant downward acceleration, which we're calling W, and its path, its trajectory, is described by this neat little parabolic equation. Our mission? Find its velocity right at the very beginning, at the origin. Let's just break this down. We're given the path, y equals ax minus bx squared. We know there's this constant downward pull, kind of like gravity, and our target is the velocity right at the start of this path. So the real puzzle here is figuring out how this purely mathematical equation for the path connects to the very physical idea of velocity. All right, so to bridge that gap between the math equation and the actual physics, we've got to pull out the right tools from our toolkit. Let's quickly go over the core ideas of motion that are at play here. Now, the problem mentions a constant acceleration along the negative y-axis. That should be setting off some alarm bells. I mean, that's the classic setup for projectile motion. The particle is basically being thrown, and this equation is just describing the arc it makes through the air. You know, the key to handling any projectile motion problem is to split it into two much simpler parts. Horizontally, along the x-axis, there's no acceleration at all, so the velocity just stays constant. But vertically, along the y-axis, we have that constant downward acceleration g. These basic equations right here describe the entire journey. All right, we have the problem's equation and we have our physics toolkit. Now for the most crucial part, putting them together. This is where the real aha moment happens. So here's the puzzle, right? The problem gives us y in terms of x, but our physics equations, they give us x and y in terms of time, t. So how on earth do we connect these two completely different ways of describing the exact same motion? Well, we can actually do it by getting rid of time altogether. First, we take that super simple x-axis equation and we just solve it for t. Then, we take that expression for t and we plug it right into our y-axis equation. After a little bit of algebra, we get a general physics equation that describes the trajectory, y, purely in terms of x. And boom! This is the aha moment. Just look at this. The general trajectory equation we just built from fundamental physics has the exact same structure as the equation given in the problem. They're both parabolas. They both have a term with just x and another term with x squared. So what does this tell us? It means the constants a and b from the problem aren't just random letters. They're actually shorthand for real physical quantities. By just matching up the terms, we can see that a is really all about the initial velocity components, and b is tied to the acceleration and that initial horizontal velocity. We've totally cracked the code. Okay, now that we've translated a and b into actual physics, we have everything we need to solve this thing. Let's go ahead and calculate that velocity at the origin. But hang on, before we start plugging things in, let's be really precise. What does velocity at the origin actually mean? What specific moment in the particle's journey are we talking about? Well, it's actually simpler than it sounds. The origin, where x is 0 and y is 0, that's just the starting line. It's the point where time equals 0. So the question is really just a clever way of asking for the particle's initial velocity, v0. So let's solve for the pieces of that initial velocity. We'll start with our equation for v, since the only unknown we need in there is the horizontal velocity. With a little bit of rearranging, we can isolate it. And now that we have the horizontal part, we can use our a equation to find the vertical part super easily. And there you have it. That's our answer. The initial velocity of the particle, expressed completely in terms of the constants a, b, and w that we were given in the first place. We've solved it. And of course, from here, we can also find the magnitude of this velocity, which is just the initial speed of the particle. You just use the Pythagorean theorem on those two components, and it simplifies down to this nice, clean expression. So we found the answer. We can check the box. But with any good physics problem, the answer itself is honestly less important than the lesson you learn from the process of getting there. And here is the real takeaway. This problem wasn't just a random math exercise, it was a physics problem wearing a clever disguise. The whole point was to look past the symbols on the page and find the physical principles hiding underneath. So, think about what we did. We took this abstract-looking equation and realized, wait a minute, this is just simple projectile motion. By comparing the form of our physics equations to the form of the given one, we unlocked what those variables really meant. And that move right there is what transformed a potentially confusing problem into a pretty straightforward calculation. That is a powerful strategy.
And it leaves you with a really fascinating question to think about, doesn't it? Whether you're looking at mechanics or electromagnetism or anything really. How many other fundamental physical truths are just waiting to be discovered, hiding in plain sight inside a simple-looking formula?